All right, it's the second day of quarantine Leetcoding challenge. Today's question is happy number. We need to write an algorithm to determine if a number is happy or not. So a happy number is defined as the following process. We start with a positive integer, which I guess is the input number. We replace the number by the sum of the square of its digits. And we repeat this process until the number equals to 1, where it will stay. So it will stay means that you replace 1 by the sum of the digits squared. That would just be 1. So that's 1 will become 1 and then become 1. So it's basically a self loop. It's just one of the number here, which is 1. Or you can stuck in some other kind of cycle which does not include 1. So anyway, it's just gonna try to repeat this process by replacing the number by the sum of its digits until we're stuck in some kind of loop. Either it's a single node sync, or it could be a circular sync without the number 1. Those numbers for which the process ends in 1 are happy numbers. So if it ends up in this cycle loops, it will be not considered as happy. Okay. So the example we have here, input is 19. So if we do this process, we'll get 81 plus 1, that's 82. And the second iteration, 82, will become 68. Then 68 will become 100. Then 100 will become 1. And once we reach 1, we will stuck there forever. And since the process ends in 1, this input number 19 can be considered as a happy number. So I guess a straightforward way of solving this problem is just to simulate this process, right? Just for any given number, we'll try to do this process. But then we have to sort of reasoning, are we guaranteed to converge to these two cases? Are there a possibility that this number will just blow up into infinity? Because we do notice that if we take example of this number 18 here, if you replace the number by the sum of the squares, you become 82, which is larger than 100. And for some numbers like 68, it will become 100. So that's larger than the number itself. So we need to just at least show that this thing will actually get converged. This process will actually get converged. So I guess the way of thinking that is, let's say that if you have a one-digit number, the largest you can have is 9. So the largest replacement you can have is 81. And if you are 2 digits, 99, the largest replacement you can have is 81 plus 81. So that's 162. And if you are 3 digits, the largest that you can have is 200 plus 82, 81, that's 243. And if you have 4 digits, the largest replacement you can have is 300-ish. So the replacement, the situation that when the replacement will be larger than the input number itself is limited in the case that's under 3 digits. When you go up to 4 digits, you will never see this kind of replacement larger than the previous number. So this is just a sketchy of showing that for arbitrarily large number, it will eventually get down to 243, and after that it will just be 2 cases, whether it's equal to 1 or equal to you will be stuck in a loop that does not involve 1. So I guess for the cases that under 243, we can just argue that you're likely to be limited time steps that we can determine it's in either one of the situations. So the time complexity, once the number hits below 243, we can argue that's sort of like a constant. In the worst case, we could just pre-compute everything that's under 243, and once it's in there, we just look it up. So we have some overhead to do, but when you have any input number, we can sort of argue that once it's below 243, it becomes constant. So the difficult part to figure out the time complexity is how many steps we need for the input to become smaller than 243. Into the known cases, if you will. I guess let's just take an example of maybe a number that's let's say it's 6 digits. 6 digits, n equal to 6. The largest replacement it can has is if every number is 9. So that's 81 multiplied by n. Right, that's the now n equal this thing, and the number of digits it has is log 10 to n, right? And the largest replacement it can has is this thing, 81, which is constant multiplied by log base 10 to n. So the effective size of reduction that we can go from input of size and input number with n to the next number replacement is the worst case is to reduce it to a constant multiplied by log n, and the next number replacement we can have is a log 10 of this whole thing. So that would just be dropped because that's a higher order terms in terms of time complexity. So we can say that the input number is n, the runtime complexity for doing this simulation is going to be log n. And for space complexity, if we are doing the simulation, in order to detect the cycle, there are typically two ways of detecting cycles. One is using a hash set to store the numbers you have been through the way. Just memorize the numbers that you looked at through the way. When you encounter a known number, then you pretty much know that you are in the cycle, which is the second case. You will return that the number is not happy. That will use some extra space. That depends on how many unique numbers along the way you will have. You can argue it's log n in that sense. Similar reasoning towards this time complexity analysis. Another method is it's the bunny and turtle method, which you have basically two variables. One just looking at the next number, or replace the number by the immediate next one in the simulation process. You have another variable that's actually doing the process twice. So after each iteration, you compare those two numbers, the faster one, the bunny, and the slow one, the turtle one. If they ever become the same number, meaning that the faster number is actually one loop ahead of this slower one, then you know there is a circle. So for that algorithm, you will have just 2 pointers. So that will be 2 variables. That's just that reduce the space complexity from log n to constant. So that's pretty much the analysis for the question, I guess. Maybe another crazy one to do is actually just to go through 1 to 243 and just try to figure out all the cycles there and to just store those numbers, hard code those numbers in there, and just doing this simulation whenever the transformed number is in one of those numbers that you get by exhaustive search from 1 to 243. Once you find such a number there, you just return false, otherwise it's guaranteed to be happy. So that's the basically the analysis, and so I'm trying to recover my coding ability in C++, so I would try to code the most straightforward method, which is using a hash set. So we'll call this helper. We'll define a helper function to do this simulate this process, which takes a number as input. What it would do is to replace the number by the sum of its digits squared. So initially the result, the accumulator is 0, and 1. Determination criteria is the number is greater than 1, greater than 0, and each iteration we truncate to the real last digits, and we increment the result, the accumulator, by the real last digits squared. And for this method, this function, we just return this result. And so for memory, we will use an unordered set, I guess it's called, which store the integers of the numbers we seen so far during the simulation process. We call it sing. At the beginning, we insert the input number into it, while the number is not 1. If we ever terminate this while loop, it means that the number is happy. We return true. Otherwise, we will just return false. So in this loop here, what we will do is nope. Yeah, sorry. My logic got stuck. Yeah, my code is too slow than my thought. So yeah, I need to recover my C++. Let me just stop talking and code this question up and talk a little bit afterwards. Insert the transformed number, which is n, and we need to find whether we can find this number or not. I think it's sing.n, right? If we couldn't find this number, we would insert that. Otherwise, we'll just return false, because that means we stuck in the cycle. Once we reduce the number to 1, then we are pretty much the number must be happy. So, oh shit, I'm blocking all the code. Yeah, well, I don't have time to re-record this thing, so this is the code. Yeah, basically we have a helper function to do this, simulate this process. We return return the sum of the square digits of the given input number, and the main logic here is that we use a hash set to store the numbers that we seen throughout the simulation process, and if we find the number in the known numbers along the way, then we must hit starting to enter the cycle. Then then we just return false. Otherwise, we just memorize that number. Oh, here we need to do the simulation. Simulate and yeah. So it looks sort of right to me. Yeah, am I blocking anything? No. Okay. So yeah, this time you should fine. You should be able to see the code. This is not the optimal solution. It's just the pretty much the beginner, most straightforward solution. You can improve upon using the faster slow pointer method, or maybe go hacky and just figure out all the possible cycles below 243 and hard code that. That you would just get that method. You still have to at least hit the entrance of those numbers. I will argue that the time is still log n, but it's constant space. So let's submit this. Compiling error. What I have here. Use of undeclared identifier for n. Oh, okay. Let's just do a quick check. This time looks fine. Okay. Yeah. That's the daily challenge for today.